Welcome to the Code Navigators. If you're looking for a really solid, structured walkthrough of the International Code Council codebooks, you're in the right place.
Absolutely. Whether you're prepping for an ICC exam or, just trying to get your head around a complex topic for a project, we're here to help.
Our goal is to guide you chapter by chapter, explaining the core concepts and, maybe more importantly, showing you how to find what you need fast.
And we should be upfront about our process. This discussion is generated with AI assistance, but it's all meticulously structured and then rigorously reviewed by a human code professional.
We're focused on getting you information that's accurate and actually useful.
And before we get started, we have to do our legal reminder. Please remember, this is all for educational purposes only.
Right.
It is not a substitute for professional advice or, site-specific engineering judgment. You absolutely must consult the official current ICC code edition for today. That's the 2021 IBC, and a qualified professional.
Always.
We're just reporting on the content of the codes. We're not stating any copyrighted material.
Okay, with that out of the way, let's unpack this. Today, we're navigating Chapter 15 of the 2021 IBC, Roof Assemblies and Rooftop Structures.
And this chapter is so much more than just shingles.
Oh, for sure. It's really the comprehensive manual for the building's hat, isn't it? The thing that protects everything below from the elements.
That's a great analogy. It really is. Because it covers everything from the deck itself, the weather protection, fire resistance, and the structural integrity.
So for anyone studying, our mission today is to break down these key sections. We want to pinpoint where the code shifts from performance requirements over to, say, specific material rules.
Exactly. And we'll highlight the critical tables you really need to master.
All right, let's get into it. We start, as always, with the foundational stuff. Section 1501, General.
Yeah, this is the standard IBC setup. It just establishes the scope that this chapter governs: the design, materials, construction, all of it. Pretty straightforward.
But then the real action kicks in almost immediately in Section 1502, roof drainage.
It really does. And this is so critical. A lot of catastrophic roof failures, they don't happen because the shingles blew off. They happen because the structure collapsed under the weight of water it wasn't designed to hold.
And preventing that is the whole point of this section.
Precisely.
So we start with 1502.1, primary drainage. This just says you need a primary system, right? Roof drains or scuppers.
Right. And it has to be designed according to Section 1611 for rain loads and also Chapter 11 of the International Plumbing Code, the IPC.
But here's where it gets really interesting, and I think this is a big one for inspectors. Section 1502.2. Secondary drainage.
This is huge. Secondary, or what you might call emergency overflow drains or scuppers, they are mandatory.
Mandatory on any roof where water could potentially pond.
Exactly. And they have to be sized to make sure the water depth never, ever exceeds the design ponding load that the structural engineer specified.
Now, so what's the number one rule for these secondary systems?
Yeah.
It's that they have to be separate, isn't it?
100%. They have to be completely independent of the primary system.
Why is that so important?
Well, think about it. If your primary drain stack gets completely blocked, maybe by leaves, ice, a forgotten tool from a roofing crew, if the secondary system tied into that same pipe, it would be useless. The blockage would take out both.
So the secondary system has to have its own path out, and it has to drain somewhere visible.
Yes, somewhere visible. That's a key part. The code wants someone to see water pouring out of that overflow scupper and think, hey, something's wrong up there.
It's an alarm bell. That visibility requirement is genius. So if you're using scuppers, 1502.3 says they need an opening of at least 4 inches.
Yeah.
But functionally, the elevation is key, right? The secondary drain inlet has to be higher than the primary one.
It has to be. It ensures the primary system handles your everyday rain. The secondary system only kicks in when the water level rises to a dangerous depth, which tells you the primary system has failed or it's just completely overwhelmed.
So if an inspector sees a primary and a secondary drain at the exact same height,
that's a major red flag. The design is flawed. The secondary system isn't serving its purpose as an emergency overflow.
It's basically just a redundant primary drain at that point, not an emergency one.
Correct.
And what about 1502.4 on gutters? It looked like there's a specific fire safety concern here.
There is. For commercial buildings, so not your typical single-family house or garage, gutters on the outside have to be made of non-combustible material or at least Schedule 40 plastic pipe.
And the logic there is just to prevent fire from spreading up the outside of the building.
That's it, exactly. On a larger building, you want to minimize any potential path for fire. A flimsy plastic gutter full of dry leaves could act like a fuse, letting fire climb the exterior wall and bypass all the fire-rated construction inside.
So metal or heavy-duty plastic minimizes that risk. Makes sense.
Okay, so that's getting the water off the roof. Now let's talk about keeping it from getting in the first place. Section 1503, weather protection.
This is all about the integrity of the building envelope, and the star player here has to be flashing, right? Section 1503.2.
Absolutely. Flashing is the MVP. It's required everywhere. Every juncture, every wall intersection, every pipe or vent that pokes through the roof. If you have a break in the membrane, flashing is what keeps it watertight.
And the code is pretty prescriptive here. It has to be corrosion resistant. Minimum number 26 gauge galvanized sheet or 19 thousandths of an inch thick.
And that corrosion resistance is non-negotiable. It's sitting in water its whole life.
We also have rules for parapet walls in 1503.3.
Yep.
They need a cap or a coping on top.
Right, and it's not just the cap itself. You have to have flashing underneath it to stop water from getting into the wall assembly. Plus, the top of that coping has to positively drain. You can't let water just sit up there and soak in.
Okay, let's talk about crickets and saddles. Section 1503.5. These are the unsung heroes of good drainage.
They really are. You need a cricket or a saddle on the high side, the ridge side of any chimney or penetration that's wider than 30 inches.
So why 30 inches? What's the magic number there?
That's the point where the obstruction is big enough to create a significant dead spot behind it. Water flow stops, leaves and debris pile up, ice dams form. And it's just asking for a leak.
So the cricket is basically a small peaked roof structure that sits behind the chimney and diverts water around it instead of letting it pool.
Exactly. It keeps the water moving.
All right, now we pivot. We're moving from installation rules to engineering demands with Section 1504, performance requirements.
This is the analytical part of the chapter. It's all about making sure the roof can handle the forces of nature trying to tear it apart.
And the main force we're talking about is wind.
Wind is number one. Section 1504.1 says roof decks and coverings have to be designed for the wind loads that are calculated in Chapter 16. Now, we're not going to get into the weeds on the calculations themselves.
No, but we should explain what drives them. When you go to Chapter 16, the wind load calculation is based on three main things, right?
That's right. You have the basic design wind speed for the geographic location, the mean roof height of the building, and the exposure category.
And that exposure category is so important. Can you quickly break those down?
Sure. Exposure B is basically urban and suburban areas, lots of trees and other buildings to break up the wind.
Okay.
Exposure C is open terrain, think flat, open fields. And exposure D is the most severe. It's for flat, unobstructed coastal areas right next to the ocean.
So if you're building a tall building on the Florida coast, that's exposure D, high wind speed, your engineers are going to come back with some massive uplift numbers.
Massive. And the rest of Chapter 15 then tells you what products and installation methods can meet that demand.
Which leads us right to 1504.2, wind resistance of asphalt shingles. Shingles have to be tested to a standard, ASTM-D 7158.
And that test gives them a classification, Class D, G, H, or F. It tells you what wind speed they're rated for.
Table 1504.2 is one you have to know for an exam. It's the direct link. If your building's design wind speed is, say, 110 miles per hour.
Then you need a Class G or Class H shingle. If it's up at 150, you're in Class H only. It's that simple.
So the code translates the complex engineering into a simple product label an inspector can check on the job site.
That is the whole system in a nutshell. Chapter 16 gives you the force, Chapter 15 gives you the performance requirement, and then Section 1507 will tell you how many nails to use to hold it down.
This section also gets into low-slope roofs. 1504.5 talks about ballasted systems. That's where you hold the roof down with gravel or pavers, right?
Correct. And you can't just dump some rocks up there. The whole system has to be designed and tested per another standard, ANSI SPRY RP4, to prove the ballast is heavy enough to resist the calculated wind uplift.
And what about 1504.8, impact resistance?
That's for low-slope roof, too, is to make sure the membrane can handle, accidental damage, drop tools, foot traffic.
So when the HVAC tech goes up to service a unit, they don't poke a hole in the roof just by walking on it.
That's the idea. It's tested with standards like ASTM-D 4272 or the foot traffic test in FM 4470.
Okay, and one last one here. 1504.9 brings us back to those gravel surface roofs, but this time focuses on parapets.
Yeah, Table 1504.9 is another key one. It tells you the minimum parapet height you need based on your wind speed and exposure category.
The more wind, the taller the parapet needs to be to keep the gravel from blowing off the edge.
And the heavier the aggregate needs to be. It's all connected.
If Section 1504 was all about wind, Section 1505 is all about fire, specifically how the roof resists an external fire, like from a neighboring building.
Right, this is a huge life safety section. Roof assemblies get classified as Class A, B, or C.
A being the best, C being the minimum.
Exactly. Class A can handle severe fire exposure. Class C can only handle light fire exposure. And the testing is done according to ASTM E108 or UL 790.
The most important thing to grasp here is the link between the building's overall construction type and the required roof class, which is all laid out in Table 1505.1.
It is. Let's do a quick recap of construction types. Type 1 and Type 2 are non-combustible. Think concrete and steel. They have the highest fire resistance.
And at the other end, you have Type 5, which is your standard wood frame construction, combustible, lowest fire resistance.
So Table 1505.1 basically says that your highly protected buildings, like a Type 1A high-rise, need a Class A roof. You have to maintain that high level of fire resistance for the whole building.
The hat has to match the fire resistance of the building.
Perfect way to put it. And conversely, a Type 5B building might only need a Class C roof, or if it's far enough away from other buildings, it might not need a rated roof at all.
Now, what about modern stuff like solar panels? I see sections 1505.6 and 1505.7 address photovoltaic systems.
Yes, and this is critical. Whether you're using BIPV, that's building integrated photovoltaics that act as the shingles themselves, or you're mounting traditional panels on top, the whole assembly still has to meet the required fire classification.
So you can't just put anything up there.
No. The BIPV products are treated just like any other roof covering. The mounted panels and their racking systems have to be tested, often to UL 2703, to make sure they don't make a fire situation worse by, spreading flames across the roof.
But once we know the performance we need, wind class, fire class, we get to section 1506, material.
This is mostly an administrative section. It just says all the materials have to comply with the code and the relevant standards.
But the key here is 1506.2, product identification.
Yes. This is how an inspector verifies everything. Every bundle of shingles, every roll of membrane has to be labeled with the manufacturer, the product name, and the classifications.
So if the plans call for a Class A, Class H shingle, you should be able to see that printed right on the packaging.
If you can't, it gets rejected. End of story.
All right, now we get to the beast. Section 1507, requirements for roof coverings. This is the longest, most detailed section in the whole chapter.
It is. This is where the rubber meets the road for installers. If 1504 told you the what the force to resist, 1507 tells you the how. How many nails, what spacing, what slope.
We start with the basics in 1507.1, underlayment. This is the layer that goes on the deck before the final roofing.
And it's required under all roof coverings. But the real critical part here, especially for our listeners in colder climates, is 1507.1.2 ice barriers.
Right. These are required where the average daily temperature in January is 25 degrees Fahrenheit or less.
It's a non-negotiable geographical requirement, and the placement is a very common test question.
It has to extend from the eaves edge up to a point at least 24 inches inside the exterior wall line of the building. Why that specific measurement?
It's all about where ice dams form. Snow melts on the warmer part of the roof over the attic, runs down, and then refreezes over the cold eave overhang,
Creating a dam of ice.
Exactly. Water backs up behind it. That 24-inch rule ensures the waterproof membrane extends far enough up the roof to protect the sheathing from that backed up water.
That makes perfect sense. Now, 1507.1.3, attachment of the underlayment, brings us back to wind speed again.
It does. And the difference is pretty stark. You can see it right in Table 1507.1.3. In lower wind zones, below 140 miles per hour, you basically just need enough fasteners to hold it in place while you work.
But when you get a 140 miles per hour or more,
The game changes completely. The code requires fully adhered or mechanically fastened patterns. We're talking corrosion-resistant fasteners every 6 inches. The underlayment itself becomes a structural part of the wind uplift system.
wow. Okay, let's run through some of the specific materials since this is where a lot of mistakes happen.
Let's do it. Starting with 1507.2, asphalt shingles. Minimum slope is 2 and 12.
But there's a catch for low slopes, right?
There is. If your slope is between 2 and 12 and 4 and 12, water moves a lot slower, so you need extra protection. That means a double layer of underlayment.
And fasteners are super specific, minimum 12-gauge nails, and they have to penetrate at least 3/4 of an inch into the roof deck.
That penetration depth is all about withdrawal resistance. It's what keeps the shingles from getting peeled off by the wind.
Okay, what about 1507.3, clay and concrete tile?
Minimum slope is 2.5 and 12. The big challenge with tile is that it's heavy, and the individual tiles can act like little sails in the wind.
So attachment is everything.
Everything. And this is another one where you need to know the table 1507.3.7. It tells you the attachment method based on wind speed and roof height. In low wind areas, a couple of fasteners might be fine.
But in high wind, high-rise situations,
The prescriptive rules go out the window. The attachment system has to be specifically engineered to resist the calculated wind forces.
that's a pattern we see a lot in the code. Low risk gets a simple recipe, high risk requires an engineered design.
Exactly right.
Let's touch on metal roofs, 1507.4 and 1507.5. It's a big range of minimum slopes here.
There is. Metal shingles are similar to asphalt. They need a 3 and 12 slope. But some lapped, non-soldered standing seam panels can go all the way down to a 1/2 in 12.
And that's because the seam itself is designed to be watertight, not just shed water by gravity like a shingle.
You got it. It's a monolithic system.
What about traditional materials like slate? Section 1507.7.
Slate needs a minimum slope of 4 and 12. The key detail there is the headlap. How much the upper course of slates overlaps the course 2 rows below it.
And that changes with the slope.
It does. On a shallow 4 and 12 roof, you need a big 4-inch headlap. But on a super steep roof, 20 and 12 or more, water is moving so fast that you only need a 2-inch headlap.
That's physics in action.
Pure physics.
All right, wood shingles and shakes in 1507.8 and 1507.9. This one has a really interesting requirement for the sheathing underneath.
It's a great example of where the code has to balance competing needs. Wood shingles and shakes need to breathe. They need to dry out.
So normally the code wants you to install them over spaced sheathing, not a solid deck.
Correct. But, there's a big but, if you are in a cold climate where an ice barrier is required.
Let me guess, you have to use solid sheathing.
You have to, because that self-adhering ice barrier membrane needs a solid, continuous surface to stick to. You can't install it properly over gaps.
So in cold climates, the need for a sealed ice barrier overrides the wood's need to breathe.
It's a design compromise you have to make.
Okay, let's quickly hit the low slope systems. 1507.0 built-up roofs.
BURs, the old school tar and gravel roofs, they generally need a minimum 1/4 and 12 slope.
But there's a weird exception for coal tar pitch roofs.
There is. They can go down to an 1/8 and 12 slope.
Why so flax?
Coal tar has a unique property where it can sort of self-heal at room temperature. It actually performs better with a little ponding water on it than asphalt does, which breaks down. So the code has historically allowed it to be installed flatter.
Interesting. And then we have the modern single plies and 1507.1p PVC, EPDM, TPO, and spray foam in 1507.13.
All very similar requirements for them. They have to meet their ASTM standards, and they all require that minimum 1/4 and 12 slope. Spray foam also needs a protective coating to shield it from UV rays.
And finally, 1507.16 brings us back to photovoltaic shingles.
Yeah.
They have a 2 and 12 minimum slope and basically mirror the fastening rules for regular asphalt shingles.
That's right. As we move on from the coverings, we get to the supporting elements. Section 1508, roof insulation.
This is all about thermal performance, but it has fire safety implications too.
For sure. 1508.1 says the insulation has to be compatible with everything else in the assembly. You don't want a chemical reaction that degrades your roof membrane.
But the bigger issue is that a lot of foam insulation is combustible.
It is. So if you're using rigid foam insulation, it has to be part of an approved fire-rated assembly. That often means putting a layer of gypsum board or some other thermal barrier over it to protect it from fire.
Sections 1509 and 1510 are pretty quick. They cover roof coatings and radiant barriers.
Yeah. Coatings have to meet their standards, and radiant barriers can't be installed in a way that compromises the fire resistance of the structure. Pretty straightforward.
Okay, that brings us to section 1511, rooftop structures. This is everything that sticks up above the main roof line: penthouses, equipment screens, towers.
And this section is all about 3 things: limiting area, limiting height, and managing fire risk.
Let's start with penthouses in 1511.2. What are the size limits?
2 big ones. First, the total area of all your enclosed rooftop structures can't be more than 1/3 of the area of the roof they're sitting on.
And second,
They can't be more than 18 feet tall, measured from the roof deck.
and crucially, 1511.2.2 puts very strict limits on what you can use them for.
Extremely strict. 10 houses are only for housing mechanical or electrical equipment, elevators, or stairs. That's it.
No storage closets, no break rooms for maintenance staff, no little offices.
Absolutely not. The code is trying to prevent you from adding another occupied story to the building without meeting all the requirements for egress, accessibility, and fire load that would come with it.
What if a maintenance team says they need a permanent workbench in there to work on the equipment?
That's a tough one. An AHJ, an authority having jurisdiction, might allow it if it's truly integral to servicing the equipment. But the line is very, very firm. If it looks like it's being used for general storage or as a workspace, it's a violation.
Okay, beyond use, the big topic here is fire separation. The construction type of the building below dictates how the rooftop structure has to be built.
This is a non-negotiable life safety issue. For type 1, 2, or 3 construction, the penthouse generally has to be built with the same non-combustible fire-rated materials as the building itself.
But there's a huge exception, a trade-off the code allows.
Yes, the 20-foot setback rule. This is so important for designers to understand.
Explain that.
If you can place your non-combustible penthouse 20 feet or more away from the edge of the roof,
You don't have to make it fire-rated.
the fire resistance rating can be reduced to 0. The distance itself provides the fire separation.
That is a massive cost implication.
Yeah.
You're trading real estate on the roof for a much cheaper construction method.
Exactly. A designer who puts a penthouse right at the building edge for aesthetic reasons, without thinking about this, just added a huge amount of cost to the project by triggering the need for 1-hour rated construction.
This also applies to mechanical equipment screens in 1511.6, right? The screens people use to hide ugly HVAC units.
It does. Let's take a common scenario, a type 3 building, which can have combustible heavy timber elements.
Okay.
If you want to build your screen out of wood, even fire retardant treated wood, it has to be at least 20 feet from the building edge. If it's any closer, that screen wall has to be non-combustible or have a 1-hour fire rating.
You can't just put up a regular wood fence to hide the AC units if it's near the edge.
Nope.
And there's a specific rule for low screens on type 1 buildings. Even if the screen is less than 4 feet high, if it's within 20 feet of the edge, it still needs that 1-hour rating.
The code is really protective of the perimeter integrity on those high-rise, non-combustible buildings.
So last up in this section is 1511.5, which deals with towers, spires, and domes. They're treated a bit differently.
A little bit. They still have the 1/3 area limit, but they're allowed to go much higher, up to 45 feet above the building's highest point. They're seen as more decorative, not occupiable space.
All right, our final section to navigate. 1512, re-roofing. This is huge because most roofing work is on existing buildings.
It is, and re-roofing breaks down into 2 main categories. Roof recovering in 1512.3, which is putting a new roof on top of an old one.
A layover.
Right. And roof replacement, which is a full tear-off down to the deck.
You're generally allowed to do a recover, but there are 4 big conditions in 1512.2.1 where you absolutely cannot.
Let's run through them. First 2 are about the existing condition. You can't recover if the old roof is water-soaked or if the deck underneath is cracked or rotted out. That's just common sense.
What are the other 2?
The third is about layers. You can't violate the material-specific limits. For asphalt shingles, for example, you can only have 2 layers total. If there are already 2 up there, you have to tear them both off. You can't put on a third.
And the last one is a fire safety issue.
It is. You can't create a new concealed combustible space. So if the existing assembly has, say, old wood shingles, you can't just cover them up and create a hidden fire path without some kind of protection, like a layer of gypsum board.
So you have to assess the condition, count the layers, and check the fire integrity.
And this is so important. 1512.2 ties everything back to our first topic.
Drainage.
Drainage. If you do a recover or a replacement, you have to bring the roof into compliance with the secondary emergency overflow drainage requirements.
So that's the trigger. An old building might be grandfathered in, but the minute you do a major re-roofing project on it, you have to add that secondary drainage system if it doesn't have one.
That's the mechanism the code uses to upgrade safety over time. Every re-roofing job is an opportunity to fix a critical deficiency.
And that's often why re-roofing jobs need a structural review too, right? Adding another layer adds weight.
A significant amount of dead load. You have to make sure the existing structure can handle it.
Okay, I think we've made it through. That was a really thorough navigation of IBC Chapter 15.
We covered a lot of ground.
We did. We started with the absolute necessity of water management in 1502. Then we moved through how wind and fire performance in 1504 and 1505 really drive the entire design of the assembly.
And we spent a good amount of time in the weeds of Section 1507, hitting the details for everything from wood shakes to coal tar pitch.
Yeah.
It's all about making those conceptual links. High wind speed means specific nail patterns. Type 1 construction means a Class A roof.
And Section 1511 on rooftop structures really highlighted that critical trade-off between design choices and cost. That 20-foot setback rule can save or cost a project a ton of money.
It really can. This brings up an interesting question to think about.
Go for it.
Given all the extreme detail in Section 1507 about fastening, especially for high wind areas, how does a general contractor really ensure compliance on a fast-moving job site? Especially now when materials get substituted so often, the code demands adherence to a tested assembly, but verifying that in the field, with all the pressures of a construction schedule, requires absolute vigilance.
That is a fascinating challenge to chew on. Something for everyone to think about in their own work.
For sure.
If you found this breakdown valuable for your studies or your professional work, you can support the Code Navigators. It helps us continue our mission to make these complex codes clearer. Just visit the Patreon link in the show description.
Your support really does help us keep creating this content.
Thank you so much for listening.